Hello, hello. Welcome. Just kicking off the stream here and with 2 minutes to spare. What? Yeah. Hello, Big Adam. Hope you're having a wonderful time today. It's still morning for me, but I don't know if it's morning for you. So, good morning if it is. We're going to be having a pretty sweet stream today. When we left off last week, we just finished assembling the hot swap controller, the ideal diode controller, and the 12-volt buck converter. But we spent a lot of time kind of debugging, actually getting it to work, because R90 was not populated correctly. So it caused us some heartburn and slowed us down. We didn't get through all the testing that we wanted to do. So basically we're going to come in today. We're going to populate the 5-volt and the 15-volt buck converter. We are going to do some load testing. We're going to be doing some line load regulation testing, efficiency, those sorts of great things. So, should be a fun time. Yeah. The other thing that we did is between this time and last time, we got some connectors that actually fit in the board. So we're going to need to think pretty hard. Turns out these are 2.5 by 5.5 millimeter jacks, not 2.1 by 5.5 millimeter jacks, which means it's incompatible with a lot of off-the-shelf power supplies, and I'm just not sure if we're going to want to pull that forward. The reason why is these are rated for 10 amps, which is awesome, so we can get a ton of power in here for doing like the battery charging and whatnot, but I'm just not sure if that is going to be a good move long term. Alright, so that's kind of what we have on the docket for today. I was actually good. I got prepared before the stream, so I've got a pile of only the parts that we'll need to assemble here, and that should really save us a little bit of time. I'll just tweak the camera so you can see that a little better. And get the ESD strap on. I think we'll be good to go. So I now realize that this is showing offline. Hopefully I can you guys hear me? Hopefully you can hear me. It said offline, now it says live. Hopefully that's working. Guess we'll find out. Oh, okay, good. Glad it's working. Awesome. Okay, so got the list of parts here that we need to assemble. Just got it kind of color coded by the order that I want to do it. We're gonna come in and do the silicon stuff first, and it's really just because that stuff's pretty low profile and can kind of be difficult to do after the fact. So yeah. In fact, I think we'll start off with our transistors. Put this off to the side. Yeah. So last week we realized that these transistors really should be reflowed. They really just don't play very nice with being hand soldered. It doesn't flow well underneath the thermal pad. So what I'm doing is I'm just, rather than using solder paste, which I do have, it's just pretty old, rather than using that solder paste, I'm just going to tin those pads, and then we'll put on a dollop of flux before we populate those parts. Need to find our transistors. I think it's that one. I'm gonna do these first because these are the only parts that really need to be reflowed properly. DIY reflow oven. They certainly get the job done. They generally don't follow a reflow profile as well as the commercial ones, so if you have something that's really sensitive, it might damage something, but I think most of the time it would probably be okay. The biggest hang up with me on a DIY reflow oven is that if you're making a DIY reflow oven, you probably don't have a pick and place machine, and so you're going to be placing all these parts by hand. And if you get a little, well, basically what I'm trying to get at is that it seems somewhat likely that if you don't have a pick and place machine, you'd be placing these all by hand. Maybe you like bump the board and knock half the parts off. It just seems pretty. I've heard some pretty fun stories with that where people wasted a lot of time. And it's like, if you're gonna place everything by hand and knock off half the parts off the board, would it have been faster to just solder it by hand? I don't know. For me, probably. You can whip through parts pretty fast once you get in the zone. And if I really, really needed to like reflow something, I'd probably be building a lot of them. If you have a DIY pick and place machine, then by all means, DIY reflow oven. Maybe that's a better way to say it. I have nothing against DIY reflow ovens. Do whatever it makes the most sense for you if that's, yeah, pick and place and reflow because you want to build hundreds of things. Do it. I don't know if I'd recommend it for something like this. We're building a one-off. I don't know. Guess we'll see. The clock's running. We'll see how long it takes. Alright, that pad's starting to get nice and warm. Try to keep my hand out of the way. It's not quite ready to go. Oh, it's close though. Alright, part is placed. Alright, just gotta get her heated up a little bit. Want to get a little more flux on there. Wonderful. Alright, round 2. This one should go pretty quick. Yeah, starting to... oh goodness. Alright, now that one placed. A little bit of flux. Oh goodness. Kinda knocked it off the pad there. This one's not quite ready, not quite down. Alright, I think that's good. We'll find out in a moment. Maybe I'm conflicted about DIY reflow ovens. Maybe that's the... I'm not sure. If you have one though, if you have a DIY reflow oven, I'd love to see it. Shoot us a picture. Last 2 FETs. One thing to note, for those that haven't done hot air soldering before, it's important not to just leave it directly on top of the component lead. Like, you don't just want to blast the component or one spot of the board. You want to kind of make sure you're evenly heating the region. Helps to make sure the solder flows well. Oh goodness. Ah. I feel like we got one of those to flow well and the other one... ah, maybe we did. Maybe we did. That actually feels pretty good. Oh, getting all tangled up over here. Alright, So I'll come back and finish off the smaller leads. First, let me just kind of... that does not inspire confidence. That's not soldered on at all. That's perfect. Perfect. Alright, one of these didn't get on. It's Q9. The way that it felt, it just felt like the flux was kind of loosely sticking it in place. Didn't feel like it was actually a metallic bond. Shouldn't be able to wiggle apart when it's got a giant thermal pad soldered to the board. Nope, not at all. Alright, let's just give it a little tap. Yep, that's definitely good now. Okay. We'll come in and solder the other leads. Come on now. Alright, hopefully those were the hardest. Okay. I'm gonna get the gate drive resistors in here next. Believe those are a 5.11 ohm. Check the sheet. This is R78. Yep, 5.11 ohm, 0805. That's just, yep. Good morning, WTP Gaming. Good morning. Yeah, we are just getting things kicked off in the lab this morning. Assembling a couple buck converters. Gonna do some sweet electrical testing once we're done. Should get through this pretty quick. Yeah, it'll be a good time. It'll be a good time. How are things going on over by you? Hopefully nothing too crazy. It is a Saturday after all. Oh boy, I gotta clean off these tweezers. The parts are like sticking to them. There's one. There's two. Oh. Yeah, maybe we should break out the microscope. Let's get this fourth one captured nice and close. All the crazy, many projects to render. I think there's worse ways to kick off a Saturday. Sounds productive at least. Sounds like you're getting things done. But sorry that it feels busy. Yeah. Just gonna come in here, get the soldering iron on both the part and the pad, finish her off. Awesome. How does that look? Does that look like I got it? That's pretty hard to tell. D37, missed a little bit. R78. That's the side. Oh boy, my camera is like super not right side up. Alright. Oh. There we go. Oh boy. Sorry about the earthquake. That was really throwing me off. Yeah, that looks like that flowed pretty well. Just take that little. Alright. Got one more there. R79. Okay. Oh, I love that. I love that close-up view. That's something special. Okay. So, thinking let's get our controllers on there next. See if we can't get that. This is the NCP 3020s. Just cross these off the list as we go. Got those on. We got those for transistors onto the switch mode power supply controllers. There we are. You can see a couple of them didn't survive last week. In theory, we only need 6. In practice, we've already used 5. Whoops. That's alright. That's alright. So these are kind of fun to get soldered in. There. So we kind of handle these the same way that we handled those resistors, in the sense that here, I need to shift some stuff around. 1 second. Alright, great. So we handle it kind of the same way, in the sense that we tin one pad and then you slide the part on. The way that it's different is that we have to be a little more careful. It's pretty easy to get one of these misaligned. So I just kind of get it where it should be. Notice I'm just tangent to the pad. Then we heat up that solder. Slide the part in. Just use that like glue. So now our part's being held in place. We can come back around with the solder. Make a good connection on a second pin. I'm actually just gonna go through and I'm gonna try to do this pin by pin, though we could use a drag soldering method as well. Here's one side done. Alright. Should be good to go. Round 2. Oh. Getting some interference from other parts on the board. It's alright. It's alright. Yeah, there's nothing quite like getting the soldering iron out on a Saturday morning. Puts a smile on my face. And this whole prototype is a lot of fun. Yeah, we've been doing a lot of real theoretical stuff for a while, and it's just a, let's do a gut check. Let's put this together and make sure it really works the way that we hope it will. Yeah, there's something about that that's very fun. Just getting to know the circuits better. Like last week with the peak current limiting built into this IC, and that was awesome. I don't think y'all were here for the whole stream, so I'll rehash that a little bit. But basically, there was a resistor that was populated incorrectly, and it just so happened to be one of the most critical resistors in the entire supply. And this resistor is responsible for setting the peak current limit. This does, in heavy air quotes, lossless current limiting, and I can say that because it doesn't add like a shunt resistor or anything to do the current limiting. It uses actually the RDS-on of the low side FET, which is pretty cool. Normally that kind of function's baked into controllers with integrated FETs because then they have really tight control of the RDS-on. In this case, they built it into one with external FETs, and they let you program what the voltage limit should be, which is really, really cool. The problem, of course, comes in when you populate a part that is very, very wrong. and we did. We were off by like an order of magnitude. Alright, so what do we have here? So we got D, 34, 33, and 35. Those are green. Red. Where's the blue? T47? T47. Alright. Whoa, these are green. Okay, guess we're putting these on. D34. D34. Alright, whatever. I know I need 3 of them. I'll just plop them down on the bench for now. Glad I double checked. Holy cow. Alright, so these are pretty, gotta be pretty careful with these. Yeah, I'll show you on the microscope. These have a tiny, tiny little polarity marking. So that's, well, like if you were imagining the diode symbol, that arrow points that way, so in this case the cathode is on this side. But from the top of the chip, you really can't see a thing. Oh, come on. Come on. Off. Yep, so now got our 3 LEDs lined up. Oh man. Alright, yep, these tweezers are getting cleaned. Alright, one moment. I can't even move parts around. That's ridiculous. They just stick to the tweezers. So just getting some isopropyl alcohol, one of our task wipers. Alright, let's try that again. Pick it up. Set it down. Okay, a little more cleaning required. No problem. Okay, let's try that again. All right. It's like a stickiness competition. You just keep losing. All right. There we go. Oh, nice and clean. Oh, you know what? The problem is that I have it on the part now. The part is actually sticky. Let's see if I can clean that off. Okay, so cathode side. Oh no. Trying to be very careful because getting these populated backwards is a little bit of a pain. Okay, so I've got all three cathodes lined up. Let's tin that on the board. So we are populating 3 diodes, green LEDs, D34. I'm gonna tin the cathode. Okay. D33. D35. Okay. So those are the 3 resistors up here on this management circuit. Alright, so I'm gonna try on carefully grabbing one of those LEDs. We'll get that populated in a hurry. LEDs can be kind of tricky because they're made with these castellated holes, or the drilled out, like it's a circular hole that's cut in half. It can be a little tricky to get the solder to flow nicely, and what's worse is that if you hold the heat on them too long, they are semiconductor devices and they do get damaged from excessive heat. So if you need to mess around with them for a long while, you can damage them. That's why I like doing these in batches of 3 or more, because it gives the parts a chance to cool down a little bit while you transition between tasks, so you don't solder one side and the other right away. Yeah. Okay. Hopefully those are good to go. 3 green LEDs. Why not? Let's keep her going. And now we've got 3 red LEDs, D27, 29, 39. 27, 29, 39. Same deal with these. Going to tin the negative side. 27, 29, 39. There we go. Hey. Nah. Come on now. Dope. Got it backwards. Alright, spin it around. So this is where I really love having these bent tweezers. Because I'm like working around myself. It's like yeah. Intense focus required. But there we go. Got it on. No problem. No worries. It's on there just fine. After all, it is an LED. It's not exactly mission critical. And in this case, we actually have redundant LEDs because the core schematic I was copying from had an LED in it, and then we added an LED for the proto board, not realizing it already existed. So really, we only need 50% of these LEDs to work. Not so bad. Alright, what's next? Some PTCs. Why not? You can get these soldered in. We'll just go in a row. Anything else will just take longer. So these are the 5 amp PTCs used on the output of these supplies. They're actually incredibly thin for... Wow, I just realized these are marked on both sides. They don't have a top or a bottom? That's weird. Let's see if I can capture this. These are kind of tricky to get soldered in. And the reason why is simply because of their physical size. Because they are so thin. They kind of like to move around on me. Whoop. Speaking of, yes, we'll see if I can get this to play nicely. I was having an issue with getting the solder to flow across the entire width of the pad and with getting the part flush. Oh, looks pretty good. And I feel like the consequence of not getting the current to flow nicely on this part would be the current density throughout the PTC may not be as equal, and it might make it start to trip early. I don't know how true that is. I mean, it's got metal tabs on both sides. It's probably fine. Those LEDs, 10 a.m. on the East Coast, 9 a.m. Central Time. A bit confusing. Soldering is awesome. Yeah, thanks, JD. The LEDs are 0603 WTP Gaming. Hardest part of this entire project, remembering to take the yes, that will be the hardest part of this project. Yep, there will be redundant LEDs in this design until the end of time. Unless I remember. Yep. In some cases, like I don't know if you noticed, but the 5-volt supply, not only are they redundant, they're the same color. Which is kind of weird. Whenever I make decisions like that, there's 3 LED colors in the design. And I basically just picked one at random. And I was like, yeah, red feels like my color for the 5-volt supply. I'm just feeling like 5 volts is red. And I came to that same arbitrary decision, that same arbitrary conclusion twice. I was a lot less decisive with 12 volts and 15. Because I think I picked green and red for the 12. I don't know. We'll see when we power it on. Alright. Fuses. Moving on. Alright, let's mark off those couple components. So we did these 3. We did these 2 fuses. The ferrite beads are done because we actually did this last week. Okay. Got 24-volt TVSs. I'll mark those off even though they're not on yet. Doing those 3 next. This is 36. I think I know where these go. 44, 46, 36. Yep. Basically anywhere where the input voltage comes in. Protecting the controller, mostly. That's what these are for. The controller's rated up to 28, I think. So we just added some clamping diodes to make sure we're not violating input voltage requirements. Some flux is used. Yeah, I've got the flux here, and there's flux baked into the solder. Yeah, flux definitely helps the solder flow though. So I like to keep a tube on hand. There's a paste flux and there's like a liquid flux. I generally prefer the paste. Just personal preference, they all work. This is nothing special, it's just MG chemicals, no clean flux. Gets the job done. Yeah, that's the only thing I don't really like about the way that is most effective for soldering on SMDs by hand. And it's that you've got to come back and make sure you get enough flux on that first lead, and if you don't, it could lead to a brittle solder joint or something that's really susceptible to vibration. Yeah. I don't know. I feel like they do it a lot. Like it's like an extrusion process, because it's like a bead of it, usually like a star pattern where it's got 4 openings filled with flux. Yeah, I'm not sure exactly how we could demonstrate that. Maybe we'll have to try, because the nature of the beast is that the solder always kind of like seals itself off, kind of locks the flux in once it hardens. And I feel like if we cut it, we'll like crush the tubes and you won't really be able to see it. But yeah, maybe if I like file it away or grind it away, maybe if I mess around with it long enough, I can figure out a convenient way. All right. 48. W4537. These are part of the gate drive network. Establishing asymmetrical gate drive on the high side FET. Yeah, it's a good point. I wonder how they do get that in there. That flux. Yeah, that machine's, whatever machine they're using to extrude that's pretty interesting because it's got somewhere like a hopper or a vat full of molten solder. I presume there's molten solder involved. Kind of like a selective solder, wave solder machine. They're just neat. Something about being around a giant pot of molten metal that's just interesting. Alright, so we got some comparators. Gotta do some of that fine pitch work. There we are. U20. Let's see what I can do. I don't know if I'm going to be able to solder all those pins individually. This might be the one that makes me use the drag soldering method. Those pins are very, very close together. Like, compared to the size of the tip of my soldering iron. Yeah, those pins are pretty big. When we're zoomed in this close, it looks like I should approach it from the other side, you know, do it on the pins that are further apart. But there's some giant through-hole PTCs that are gonna get in my way when trying to solder from that side, where I can get the tweezers up and out of the way really easily. Oh goodness. Oh boy. Okay. It's not exactly straight. It's pretty close. See if I can finish this off without causing a short. One pin. Two pin. Oh my goodness, I've done it. Yep, it's on. It's not pretty. I'm pretty sure that's a solder defect in more ways than one. But it's on. Let's try that again. See if I can get this one on without adding way too much solder on. We added way too much solder on that. Actually, this could be a good application of reflow. Maybe I'll do that. Just adding a healthy dose solder. my substitute for solder paste. Solder paste is neat because it's got the flux baked in there. Rather than do that, I'm going to come in with the applicator. Yeah. Hi Norcorp, welcome. J-tip, toaster, reflow ovens, can get 230. IR, modified from eBay, sounds like a good idea. Pick and place first, yeah. Cool. Yes, absolutely, you have to abuse the surface tension reduction with flux. It's the only way to do it. Just drown it in flux and go. I feel like this is going to be a much prettier solder joint when we're done. Oh, come on. It's not quite straight. There we go. She's on. Okay, a little bit of flux. Gotta get the part kind of right. Dope. Got my tweezers sticky again. Have to clean those off. Come on now. Oh no. Terrible. This is what I'm working on. Trying to not melt the camera while I do this too. Yeah. Come on now. Just being stubborn. There we go. Let's get a nice close-up on those. Sorry about the farting around here. Get it in focus. Yeah. Let's come at this from a more shallow angle. There we go. Yeah, that doesn't look half bad. Yeah, that looks pretty good. Looks like we got solder on all those. I don't know about that third pin. That third pin just kind of looks like it's sitting on top of the solder. I'm not happy with that. I'm not happy with that. We'll touch that up. Alright, couple more. Alright. Hopefully those survived all that. Is the humidity high there? I don't think so. I don't think it's especially high. It's not especially low, not especially high, it's just average. Alright, blue LEDs. Yeah, I think it's more likely that incompetence is messing with the soldering more than anything else. It's the other thing about this flux is that it's a little older than it should be, because I don't know, maybe I'm just that way. So yeah, it's very, very possible that the fact that the flux is older than it should be is messing with its ability to reduce surface tension. I know my paste is very, very expired. I think this stuff isn't so bad. I think it's lasts a little longer. Where paste is very particular. So you got to keep it refrigerated if you want it to last a while, and even then I think it only is rated for a year if you're storing it in a temperature-controlled refrigerated environment. Which I don't know about you, but I don't want to go sticking solder paste in my fridge. Seems like a bad time. I would not recommend putting solder or anything related to soldering anywhere near food that you intend to eat, because yeah, obvious reasons. I hope that's for obvious reasons. Flux is bad. Don't eat it. Solder is also probably not great for your health. Yeah. I don't know if reels of solder, I don't know if this solder is rated for like a shelf life. Probably longer than we'll ever really need. Alright, got our 6-volt TVS. Really, 34 of these. Where in the world did I use all those? Yep. My big goal for today is that we don't waste a bunch of time by populating a part incorrectly. I really want to get to the fun tests that we had planned for last week. I really want to make sure we get to that today. All of them. I want to know the efficiency of these. I want to know. I get really excited about efficiency. It just tells you so much about how the design works. You know, it's like there's a lot of indicators of how well a design works, but efficiency is just such a broad stroke that tells you so much. It's like, if your efficiency is 95, 98%, you can be pretty confident that everything is working well. You know, it's like, if your gate drive was messed up, you wouldn't be getting 98% efficiency. If your FET's damaged, probably wouldn't be getting 98% efficiency. There's a lot of cases where the end result is you're probably not going to be getting a very good efficiency. Sorry. Apparently I'm 12. Alright, the rest of these parts I think are gonna have to wait a moment. I got 100 puff, 10 ohm. Let's get these installed. 100 puff and a 10 ohm. Here, let me get the scissors. Ooh. There we go. Whoa! Out of nowhere, screwdriver. Alright. 10 ohm. Where's this headed? So let's cross off. Got the TVS done. Got those gate drives done. Got the blue LED done. That's all the diodes. Got a 10 ohm resistor here. R70. Where's that headed? I'm gonna guess it's over here somewhere. Apparently not. Okay. Ah, there it is. $10 ohm, huh? That seems... Actually, I think I remember what this is for. I think this is a series element where I'm testing whether or not... Oh, we can look at the schematic. I left a note. I think it's like between the output of an op amp and the input of the next op amp. Testing to see the impact. And the 100 picofarad. Where's that headed? Flux is only... Maybe, I don't know. It feels like it's going about the same this week as last. But maybe you can tell more from the zoomed in camera. Gravity! Agreed. 100 picofarad, we need 4 of these. Alright. Those 2 parts. Done. Right. Let's get our... I think these are computation components over here. So we've got C96, 89, 89. Got a 61 in there. Yep, got a 61. 68. Guess we gotta come over here for that. 60. What? Where in the world? Where do these other 2 caps go? So we got 89. 61. See, there's 68 and a 96. 68. 68. 68. And a 96. Oh, there it is. Got it. Oh, the feed forward. Silly. Whoop. Maybe what we're observing with the flux was just I grabbed it when I had warmed up and I'd been soldering for a little while. maybe I'm using it a little earlier, not quite in the zone. Maybe that's what we're observing. How many tons of solder are required for the project? At least 10. 0.100 nanograms? Yeah. I don't even know if there's a convenient way to measure that, but that is a great question. I'll tell you what, I've been using the same 1 pound spool of solder for probably 4 years. So if this is one project and this spool has lasted 4 years, yeah, not very much. I probably use more solder tinning the tip than actually makes it on the board. That would be my guess. Yeah. I think JD said it well with the 0 point, a lot of zeros, and then a 1 ton. If we have to list it out in tons, just make sure there's a lot of zeros. All right. All right, those 4 caps look awesome, as does the resistor. Time for the popcorn parts, I believe. I believe that's all the critical parts. 100 nanograms. Well, maybe that's too many zeros. Probably at least 1 gram. So we got the 100 pico. Okay. Oh, yeah, and we got those on there. Yep. I'll start with the caps because that requires less trays. We can just pull that out. Okay. Let's start with the big bulk of them, the 2.2 mic. So we got, is that 57 on there? Yep, so we've got 1 of each for our comparators. C46 on there too? It's gotta be. C46, yep. Pretty much know if it's in one of these circuits and it's an 0805, it's going to be this part. Almost certainly. Okay. Just gonna tin this. There's a lot of these parts. I think I went a little nuts with the bulk capacitance. It's getting hung up on the fact that like the voltage bias characteristic of MLCCs. It's like, well, if we apply, I forget these are, I think these are 25 volts. If we apply 24 volts on a 25 volt cap, we're gonna have like 10% of the rated capacitance. Better throw down 50 of them. Yeah. MLCCs don't really need any derating on the voltage. It's just their effective capacitance quickly becomes unusable. Nice 200-gram reel, no core pad, 3 years. About a kilogram last time. Started for a while now. What width solder is that? Yeah, I've got a 0.2 millimeter. No, I got a 0.3 millimeter. So you were right on there. And the other one I've got is a 0.032 inch. So you have to convert that. They don't give it in. No, they don't give it in the right units for direct comparison. I really like that fine solder. It is essential. People often think that you need a really fine tip soldering iron to do fine tip surface mount component soldering. Not true. You can do 0.5 millimeter pitch micros with 1,000 pins, as long as it's not BGA, if it's a quad flat, and you can solder that with a massive chisel tip, no problem. Not a problem at all. The problem is when you have too much flux and you just short out all the pins, or too much solder and you short out all the pins. There we go, we're flying. Now, just keep me honest, guys. If I put anything other than 100 kilo ohm resistor down on R98, I'm gonna be very disappointed in myself. I like triple checked that it came out of the bomb export right. I was like, all right, let's double check this schematic. Is it supposed to be 100K on all three of these? Yes. Okay. Ooh. That was about 0.8 millimeter. Yeah, so we use almost exactly the same. Almost exactly the same solder bits. Yeah, it's a great combination, right? I love, what did you say it was? 0.8? I love the 0.8, though sometimes it's a little big, so I think 0.7 would be fine, but the 0.7 in combination with the 0.3 is a strong combo. Because if you're doing something that's like a giant through-hole part, you need to get a lot of solder in there, and the flux to solder ratio is a little bit better for those types of through-hole, or like tinning wires, that kind of coarse work. Generally, that bigger solder is going to be the right size. But then, of course, you're doing the tiny surface mount parts, and you just need something with a little more finesse. Break out the fine solder. So, yeah, awesome. It was just a place where I was experimenting with different sizes, and this is just kind of where I ended up. Oh no, this cap doesn't want to take solder. It's just going on the cap. It's not actually flowing onto the pad. Oh boy, that means my thermal relief is ineffective. I'm going to need to preheat the board to get that soldered on. Or I'll need to apply so much heat to the cap I'll crack it. Alright, let's just preheat the board. Alright, so silkscreen, I'm not sure. Did you mean silkscreen or solder mask? Silkscreen is like the white text. Solder mask is the green color. I did green in this case because I needed the boards fast, and it was an extra lead time to get any other color. So like, yeah, we can spit out a green board in, I think it was 1 day turn for no additional cost. They were like, or you can pick any color under the sun and it'll take like 3 days or 4 days or whatever. So yeah, when we're building the final, the old UPS board, the Gen 1, I guess I'll call it the Gen 1 UPS board, that used black solder mask. That was pretty cool. My only gripe with the black solder mask is that solder like stuck to it, and that might have been the specific black solder mask I was using. But yeah, it's just not my favorite to work with. Alright. A little bit of reflow never hurt anybody. Come on now. There we go. Alright. That cap is super not soldered down. It's probably hot enough that if I come in with the iron, we can get this sorted in a second. Oh yeah, that's soldering like butter now. Funny how that works. Come in. That's why some people like to solder using, there's like preheater things you can get from Weller or Hiko. Y'all usually have them. Alright, we're gonna call that good. Okay. What do we got? In your opinion, largest K-tip applicable for drag or J-tip point to point? Screwed up a thermal relief before and ended up with these. Oh, 3 irons? Holy cow. Yeah. Yeah. If you don't have enough thermal relief, you can easily have a bad time, especially in desoldering, because it's like when you're doing reflow, if you're putting something through a reflow oven, everything goes through the nice process. Everything's hot. Everything just works. If you've got thermal imbalance, that can be a big problem because you'll get things like tombstoning. But as long as the thermal load is balanced across the component, yeah, you don't really need thermal reliefs to get it on. But if you want to, like, you know, rework it with a soldering iron or remove the part and populate a new one because it broke, that's where the thermal relief matters. I'm always torn when it comes to like FETs, because in one extreme, when I'm soldering, I want that part to be as thermally isolated as possible. And when operating, I want it to be as tightly thermally coupled as possible. How the heck do you resolve that? Conflicting requirements. But it's not so bad. Just gotta meet somewhere in the middle. Follow the guidelines. It'll be fine. Yeah, just gotta load up the extra caps. I just dumped out a whole bunch on the bench, and yeah. Yeah, something like that with the conflicting requirements. Usually the result is get over it, follow best practice, because there's been a lot of optimization done. SMD crystal fight like that. JD, you want to elaborate a little bit more? Fight like that, also for me. Conflicting requirements. I think that's what you're talking about, the conflicting requirements. Is that like trying to keep the parasitic capacitance down? Or like keeping it really close to the micro? Usually I can do a pretty good job of routing an SMD crystal in a reasonable way. That hasn't been a huge fight for me. Alright, 2.2 mic, that's awesome. That was a big one. Right, 0.1 mic, that's another big one. Need 11. 1. Sure, we'll say that's around 11. Here's the pile. Oh goodness, super not in the frame. Still super not in the frame. What? Oh, you just can't see them. They are in the frame. Oh, they're just tiny. Funny. Funny how that works. Alright, so this is probably like most of the rest of those caps. C53, yep. C50, perhaps, yep. C50, C47, yep. 67. Oh? Is that one different? Why is that one not showing up? Is that a note pop? C. Whoa. Oh, soldering SMD crystal by hand. 150 watt iron or preheater. Multiple irons work. C. Yeah. 52, 51. I am super not seeing some of these parts, which is kind of scary. 55. 54. What? I thought I laid these out like the same, and yet there's a resistor where a capacitor should be. C49. Yep, there's a C49. Got a C48. Yep. Alright, is that actually all 11? We got 1, 2, 3, 4, 5, 6, 7, 8. Nope. 9. 10. C91. Nope. R95. Nope. Oh boy. Where's that last cap? Come on now. How am I missing one? Alright, let's cross them off. Which one are we missing? Okay, we got C55. Yep. 49. 52. 53. 47. 50. 54. 451, 48. C 90, 62. I was just bad at counting. Yep, we got them all. Let's get them on the board. Okay. I can't remember if I baked hysteresis into these comparators or not, but if we didn't, I might be able to demonstrate why that's important. Get these things to oscillate, or at least try to. Could be kind of fun. The idea is that the input bias current can actually change very slightly on the inputs of the comparator when it changes state. And in doing so, it can actually make it flip to the opposite state and just oscillate for a little while. If you're using that to drive like the interrupt pin of a micro, something like that, can be a bit of a problem. If you're doing something like battery monitoring, it can also be a bit of a problem. Okay. That. Before I move away from this area of the board, I want to finish off these parts. Oh, come on. Don't make me preheat this part too. Alright, we're preheating this part of the board. Which comparators are those? These are MIC 7221. I think that's all you need. But if you need more, it's MIC 7221 YM5-TR. They're pretty cheap. Pretty good. I think they're reasonably low power. Reasonably low input currents. Yeah, like always, it's been a little while since I designed the circuit and did the analysis, so I can't remember everything perfectly, but I usually try to make reasonable design decisions, so like, it's probably not the worst op amp or comparator. It's probably a reasonably good value. Ooh, trying to not melt these PTCs is a little tricky. They are very tall components. Got the part number, 600 nanoamps versus 7 microamps. I'd be curious to see the cost delta on those. Wonder how similar they are in cost. Yeah, I mean, this isn't a particularly low power design either. So if it was like even 50 cents per comparator, I don't know if I'd pay the difference, because when you're feeding, 240 watts into a design, I'm not going to get hung up on every nanoamp. Johnny 5. Nope, not me. Don't know. Is this like a pop culture thing that I should know? Probably. probably. Okay. Yep, looks like we're preheating the board again. Wow, I did a terrible job of thermal reliefs on these parts. Note to self, better thermal relief on the MLCCs. A movie thing. Short Circuit, 1986. Cool. I haven't gotten into old movies. I've gotten into old TV, like Hogan's Heroes, MASH, Andy Griffith. I haven't quite gotten into old movies, but there's just something about the humor and something about it just makes me laugh. I really enjoy it. Alright, there's the 0.1 mics. I think that's probably most of them. And that was a huge bucket of parts. Alright. Couple more of these. 8200 pico. Let's stick to the caps you got here. Get the one mic. Just need 2 of these. Great. Where are these headed? 9163, C91, C63. Bootstrap caps for high side gate drive. So, kind of fun fact, when I was prepping for this stream, I was like, hey, I built these. Oh, I think No Corp and tested JD. I don't know if you were here, but I fixed it. I got plugs that plug in, so we can actually plug them in today. Look at that. But so I finished that. I was like, oh, we'll just appreciate the 12 volt regulator, and so I go and power it on. And I'm getting 24 out of the 12 volt supply, and I was like, what? Yeah, for some reason the high side FET failed short. So I don't know if we just smoked the thing during the overload, and like I saw some smoke come off the board, but I thought it was just flux. Maybe it wasn't just flux, maybe it was actually the part giving up the ghost, but yeah. It was all 3 terminals shorted together. Usual nonsense. And I was like, oh, I see a fun comment about comparators or op amps. Let me get this. Get this down. Alright, what do we got? 6541 is a 70 Australian per unit. 61, so almost the same. Yeah, I'm using open drain. The reason why I'm using open drain, I don't remember. One of the circuits required it, and so I picked the part as open drain, and then the rest of them, I just didn't really need push-pull, so I didn't use push-pull since I already had the open drain version. Yeah, I'm doing a much better job of part consolidation across the different boards, across the different designs this go. Just go around. It's awesome. It's one of those things that's really, really hard to execute because it's so easy to get tunnel vision and think, oh, I need this part, or this part's more convenient right now. But sometimes it really doesn't matter, and you're like, well, either of these will work, you know? And when either one works, making it convenient for you to see what you've already done, it's kind of tricky. All right, so now we have 8200 pico, and then we are done. Coming over to the 100 pico side, 82 is the magic number. I just need, what, 2 of these? I was able to use, yep, I was able to use the same compensation for both of these. That is sweet. I'm sure one of them's got more or less margin than the rest, but hey, if it has sufficient margin, I don't mind. Okay. So I'm guessing that means these are R59 to R87. Yes, indeed. Wait, C, not R. What am I doing? Yeah. Oh no. Oh boy. Oh man. Now I've done it. Shot out of my tweezers. Right into the soldering iron. I'm sure that's good for it. Yeah, it might have been O-ring. I think it was like an enable. Like I used them as an enable on a compensation pin of it, like a external UVLO. So it was pulling down the sync pin or the comp pin, and rather than use a push-pull to a NPN, I saved myself a part in a resistor by just using the open drain version. I think that's what it was. Screwed up on the pricing, 56 cents. Oh yeah, so it is a fair bit cheaper. It is a fair bit cheaper, but hey, that's how low power designs go. That you're paying for the extra refinement. If you really need it for the design, ultimately, you need it. So there's not really a way around it. All right, so that's a giant part. We're gonna save that one for later. I don't think we'll forget. That's a giant part. We'll do that one later. That was a terrible star. And we'll start chugging away at these resistors. Yeah. All right. What decade are you guys feeling? You want to start with thousands, hundreds of thousands, or tens of thousands? I'll throw it out there. If you don't care, I'll just pick one in like 20 seconds. But yeah, I appreciate you guys coming out today. It's nice hanging out. Nice chatting. All right, looks like we got no strong opinions. We'll start with hundreds of thousands. Whoop. Yeah, I noticed that some of these were starting to peel off. Maybe it is humid here. My label like peeled off. I don't know. Is it dry or humid that makes adhesives just fail? So if we're doing hundreds of thousands, this is the only one. JD, you pick. Yeah. Just having a bit of fun. All right. 100K. I am a big fan of these storage racks overall. My one gripe with them is that you got to be kind of careful when you're handling them, because it's very, very easy to like grab it aggressively from the test tubes and pop 5 of them out. Might try to add a handle or something to the front. It's a pretty small refinement, but just a convenient something to like set it down on. Alright. Let's see if I can get on this resistor without preheating the board. Oh my goodness. Oh my goodness. I feel like I'm just destroying this part. Thankfully it's a resistor, so it doesn't care. Yeah, maybe we should preheat the board. Big old ground pour. Yep, that's how you do it. Okay, got those on. I think he's picking no matter what. Placing to. Yeah, if you're thinking like, if that's a pick and place joke, yeah. Yep. You know, I'm semi-automated. Sure. Alright. 47 k-ohm. What? 47.5? Yeah. I keep doing that. I keep like truncating the decimal and then trying to find it in the rack and saying, what? That part doesn't exist? I can't do that. Alright, so there's the 47K5. Let's see if I can't pick another one. Actually, just gonna use my bomb print off as an organizer. It'll probably bite me. We'll try the 38K3 as well. How many of those do we need? 2 as well. I'll reach in here with the alright. So we need 101, 83. (101), 83. Get those populated. Oh yeah, but I got distracted. So I found that was shorted, coming back to the 12 volt regulator thing. Yeah, the high side FET was all shorted out. And I was like, I don't know if that was some shoot through and we need to tweak our asymmetrical gate drive. If that was just a thermal overload and we like melted the FET internally and it was just dead now. Not sure exactly what that was, but we will definitely need to keep an eye out for that moving forward. These load testing, you know, all this time where it'll just be powered on and used is great because hopefully it'll expose little things like that. If there are reliability issues, I would rather know now than later. 95, 77. Okay. Yeah. So, no corp. I think you're from Australia, right? You were looking at prices in Australian. Like Andy Griffith is an old American TV show. Is there anything like that where you're from? Like old, like 70s, 80s TV shows that just are classics and they stick around? I could get into some old Australian TV. You know? Let me know if you're aware of anything like that. Might check it out. Okay. 101, 83, 95, 77. Whoa, that was it. That was all of them. On to the ones of thousands. Okay. So we need 1.62K. These are fun. Blue. And what else do we need? 2K15 and a ton of them. We need 9. Oh, that's more than 9. That's probably 50. 1, 2, 3, 4. One, 2, 3. Sorry, counting. 2, 4, 6. Dope. Dope. Oh, it's really hard to get these flipped around. One, 2, 3, 4, 5, 6, 7, 8, 9. Beauty. Let's see if I can get the rest of these loaded back in the tube. The focus is real. Jerry Lewis. Funny movie. Check that out. All right. Oh. 1K62, we only needed 1. We need 2. Go ahead and put that back. R102. Guessing that'll be one of these compensation components. Yep. If you only need one of them, it's probably a feedback resistor. And it was. R69. 62. Guessing 63 is on there too. To 63. 72. There's a 75. 75, 65, no. 64. No. 66. No. Nope. 69. Yes. 71. Holy cow. None of those. None of those. Okay. I need a little more water. Doesn't sizzle. There we go. 100K the right size? Yes. Yeah. Yeah. I don't remember exactly why the peak current was set to where it was. I think that was just margin. I wanted to make sure I wouldn't be tripping the peak current limit. Like, that's not meant, I'm not using that to, I would never expect that we really hit that. Right? Those are the guardrails. It won't keep driving until it hits the limit. It's just, it'll let it play within those bounds, and once you hit that guardrail, it just says, nope, I'm gonna do a soft start. So it'd be like trying to mitigate shoot through, right? So if you have a cycle where you just have a short because like you drop a big capacitive load or something, that's what that's meant to save you from. So hopefully that's how it really behaves. R100, R82, nope, 81, nope. Okay. Oh wait, what? Oh no. Okay, I better start populating these because I pinned an incorrect value. Oh no, I didn't. No, I didn't. It's just R102. Okay. $100. $62. Sorry if my hands are getting in the way here. Maybe I'll do we should do a close-up. It's been a while since we switched it up. Oh my, that's in focus. There we go. See if we can get actually, you know what? Let's use this fancy. Oh, that's not much better. C56. Boom, nailed it. Can be kind of disorienting to try to move the camera. Its plane is not the same as mine. All right, 72. Tracking down the rest of these resistors is going to be really hard. Like, I genuinely, no idea where these are supposed to go. Wow, that part's just kind of floating in the air. Oh my goodness. Look at that beauty. Oh boy, that's not great. The problem is that both sides of the pads actually got some solder on it. Yikes. Time flies by when soldering. Yeah, I really liked the summary video. Just as a point, I think did a good job of like flying through the unboxing. I'm hoping I can do something like that for this as well. Just try to show the highlights, because I know that some people don't have the time or really the desire to watch this long format. So try to try to make it so everyone can enjoy. I forget who it was. Actually, I think it was tested. I think one of your comments last week was, about how to make the channel inviting to newcomers, and I really struggle with that, right? Because one of the key differentiators that I see in EEforEveryone, one of the key things that makes us different, is that we don't shy away from when math is involved. We don't try to hide the fact that it takes work to build electronics. And I think it's really easy to think, oh, I want to be inviting to newcomers, so we're gonna do like Arduino kits and use off-the-shelf modules and stuff like that. And it's like, man, there's already channels that do that, I don't want to compromise what I think makes us different and special just to be more inviting, because I'd rather invite them to join this level of the conversation. It's not necessarily square one, but I'm hoping that we can find a way to kind of bridge that gap, so they're like, hey, I really love electronics, but I really wish that my Arduino could do insert fill in the blank here. And that's where I'm hoping we can kind of get involved and find those people and get them plugged in. Get them plugged in. So 71, 72, 69. I feel like I'm missing a bunch of these. R100. Oh, forgot to solder the second side of that one. Okay. And there it is, 63. Whoa there. I do really think time flies by when you're soldering. It's therapeutic. I think it's how some people would describe painting. I don't know. It's kind of how it feels for me. Alright, we gotta track down some of these parts. We need to find R75. It's like it's just gone. I don't know where it is. R99. Oh my goodness. Oh, there's one. R99. R81. Beautiful. 99. R81. Where in the world is R75? And I really hope it was populated, because I counted out the right number of resistors. I'm out of resistors. So I might have missed by one. Populated one of these in the wrong spot. I hope not. That would be super not great. Okay. Hoping that it's in one of these clusters of parts. Actually, it could be an LED. Could it be an LED? 4, 73, 76. There it is, R75. And yes, it is populated. Great news. That is excellent. Okay. Woo! That gets a little intense. That gets pretty intense. Okay. Let's do the next two. We got a 1.62 is already done. So now we got a 5K11. need 4. There's 2. Whoa. Something tells me that these parts got contaminated. That's not good. Because I see a part with a different marking. Let me grab the multimeter, double check these. Most of them aren't used in a critical spot, but I'm counting on these being 1%. Where can I put this? Sure, there looks good. Regarding television, probably mostly old British TV shows rather than, I guess, Australian things. Other than the long-running soap operas, I can't think of anything. Oh, that's a good point. Okay, so that could be a 5.1. That could too. Alright, must just be 2 different vendors of parts getting mixed. Maybe different tolerance. Maybe one of these is a 5%. But they all appear to be 5.11K. So, alright, I gotta clean off this board a little bit. Getting stuck to things. There's just flux hanging around the board. But the annoying part is that it's getting like on my hands. I don't like that feeling. I don't like that feeling of flux on the hands. Alright. One thing I've been seriously thinking about as a shop upgrade is getting an induction heater. This is using like it's a basic soldering iron. Not that there's anything wrong with that. But I've really been thinking about getting myself an induction heated, not an induction heated, like where the direct heated, where the heating element's right in the tip of the iron. Those are sweet. They're awesome. Got a 103. Got an R53. Yep. 85. Nope. Got an 84 though. An 82. Alright. 84 and an 82. So we're gonna be. Oh, I'm barely in frame. There we go. 82. $84. $103. There we go. Parts. More parts. Well, can we get by without preheating? Yeah, I think we got it. Some of these seem to have adequate thermal release. I must have like overridden a property that I really shouldn't have. Like I adjusted the default clearance of the plane shape, but some of the parts were already placed or something. I don't know. Really depends on what you're gonna do. Old comedies I like are Red Dwarf and Black Adder. The direct heat iron? Yeah, direct heat iron, yep. You get a controller, that IEC input on the back. Ooh. That's neat. Are you saying that's the soldering iron you have? That's interesting. I'd say drop a link, but I think you'll get like banned or flagged, or maybe the comment just gets removed in the comments. That's cool. If you've got a part number, definitely drop that. I will check that out. I've been 50 is not bad. 50 is not bad. For an iron like that, direct heat iron, yeah, they just heat up so fast. That's what it is for me. You never need to wait for the thing to heat up ever again. It's just like instantly on. All right, I think we got those on. 82, 84. Those two, yup. Just a few more parts. Got the 1Ks. 7 of those. Three, 4, 5, 6, 7. And what else? We had a 7.5. So, yeah, I know there was that. I think we're gonna have to make a Twitter account. Every time I've tried a link, it's banned me for a little. Weird. I post tons of link on Twitter. And yeah, it just kind of lets me get away with it. Yeah, I was thinking about how I want to share images with you guys. Like if we're working on something and take a snapshot, Twitter just works really well. I know some people use Instagram. I don't know. I don't know how I feel about Instagram. It's just one more thing. $54. Come on. I want to try to get this one soldered on pretty quick, because this is when we're dealing with a thermal relief, but I'm just dealing with it by making that the one that I soldered before the part's in place. So we can get it nice and on there. Yeah, that looks great. But as far as the irons go, I know there was that one that was super popular. 20-30C off. Ugh. Slow control loops. Not a fan. That is not the point of getting a direct heat iron. Yeah. Not a fan. No, thank you. Yeah. There's some pretty good ones out there, though. There's some pretty good irons out there. The one that I knew was powered from like the mains brick, like you were describing, was I forget what it was called, but it was like could be powered from USB or something. Then it had like a high power input too. That was a pretty sweet looking iron. All right, hey, that's all these parts. We're all done down here. We just got a couple more to do up on this circuit, and we'll be good to go. Okay, so we got 67. Got a 68. maybe? No. 64. So this, yeah, to 65. And then we should have 74, 73, 76. Yes. Yes. Yeah, I think that's what you're talking about. The TS80 or TS100, I think that's what I was thinking of. Are those? Oh, really? Oh, that's annoying. Yeah, I don't have anything against the STM32 controllers. They're pretty good parts. I don't personally like writing code for them because I think their hardware abstraction code is not great. In fact, I think in many ways, in many cases, it's easier to just pretend like the hardware abstraction doesn't work and just do direct register access for all the peripherals. And I know I'm not alone in that school of thought. So I would never select their controller for the hardware abstraction. But when they're being used, I mean, once you get them configured, they're perfectly fine micros. So, yeah, and they'll do a great job. Some of those have like a pretty fast core and can do all kinds of fun control loops with them. Have the FPU, the whole thing. But just fighting through the hardware abstraction, it's not my favorite. They're pretty good, like just like part cost. They're pretty good though. Alright, I'm trying to solder onto this massive plane with my terrible thermal reliefs. I need to constrain that better. I give up. Yeah, taking the normal tips is huge, because like, if you're getting an off-brand iron, I don't know that I'd ever want to use off-brand soldering tips. I feel like they just burn out really fast. The TS100, the weight and the cord, like having the standard barrel jack coming in the back just seems, that doesn't seem great. That doesn't sound like fun to me. Alright. Okay. Parts are on the board. Oh, we still have caps. Dang it. Oh, dang it. I thought I was done. Couple more. I mean, who really needs input and output capacitance? Who really needs test points to hook up your design to your equipment? I mean, not me. Yeah. So there should only be 3 more spots to put resistors. Yep. And indeed, there are 3 more spots to put resistors. Gonna have to. Woo! It's getting a little tight. And this would be fine for a pick and place machine, but Grand population. I'm working around a lot of little parts. And this. Oh. Left my multimeter on. Resistor the first, resistor the second, resistor the third. Yeah, so these are some signals. Right now, oh boy, that's a big solder blob. Right now I've got them coming out of this comparator and just driving some LEDs. Those are eventually going to be going to the micro. Just want to be able to inspect them. Can't find your unit? Oh, that's a shame. Yep, yeah, maybe you could even blast the firmware from one onto the others. Cool, and that's exciting. The list of parts has a lot of crossed out lines. We just got the big obvious ones left. Before we do that, I want to take that thing that just turned off. We're gonna put it in. Continuity check. We're just going to make sure that, oh, alright, diode check mode. Let's make sure our FETs are looking good. Whoa, come on now. You should look like a diode drop. What? Didn't that just work? Didn't I just measure that? Maybe I need sharper tips. Maybe I'm not able to cut through the... Huh. Okay. That should be the way that is. That's not confidence inspiring. What in the world? Cool. That's weird. That is super weird that I can't get decent continuity on these. Alright, whatever. Let's just do a short check. Power to ground. No. 15 to ground. No. Looks good. Okay. Why not? Let's check the input too. 24 to ground. Nope, we're looking good. There is a diode going across that the other way. Cool. I think we're safe to finish populating this with our test loops. And let's see if we can do a better job of these today. I was really struggling with these last time. They're super springy. There we go. That looks great. Test loops. 5-volt coming out. Yeah, this is like the basis for our next few streams. Twitter is a go. Nice. Cool. Yeah, we're on there at EEforEveryone. Hit us up. Share some pictures of your projects and stuff. Man, I wanna like get a hashtag. I've been trying to think of a good hashtag that we can use for when we're sharing projects or something like that. Yeah, I don't know. Do you guys have any ideas? Just something that's like recognizable that we'll be able to kind of hold on to. I'm open to ideas. Okay. So I believe those are the only test loops we're gonna need. Put the rest of these back. Looks like one of those is not functional. Okay. Got the test loops. Let's solder those in. Yeah, these go in pretty easy. Yeah, we'll have to find a smaller test point to use on our final design. Like the Keystone 5015s are huge. They're just absolutely massive. I don't think we're going to want to use those. But these really aren't that much smaller either. Like, these are giant and they're through hole. I just don't know. This claims we're going to need six of these. There's 6. All right. 6 of those and a couple inductors and we're done. Time for the fun testing, I suppose. We'll have to get the lab kind of reconfigured a little bit, get some of the solder stuff out of the way. Some of the other stuff in the way, but should be a lot faster than last time. I've got it all kind of where it needs to be. Should be a pretty fast transition. All right. Let's start with the inductor. Get these two on. Is it gonna bother you guys if I populate these like twisted from one another? Hopefully not. Cause I'm really feeling this orientation right now. Looks good to me. Nice and centered. I'll use some of that big solder for this guy. Whoa. Whoa. This thing's all over the place. What in the world? Can't this thing just solder on either side? That'd be awesome. Just kind of stuck there. What's going on with that? Whoa. Oh boy, this one too. Oh man. Cool, there it is. It's on. It's not pretty. Oh boy, sorry guys. Framing. It's a little crooked, but it's on. Alright. We'll get these caps soldered on. Okay. Whoa. Whoa. There we go. Cap the second. All right. Yeah, we'll see. Maybe next week I'll have to solder this together before the stream. Jump straight to the fun part. But I appreciate your patience with me while I get this thing populated. Just feels like it takes forever, you know? At least that's how I'm feeling at this moment. Then again, it is nice just to chat while we solder it. Now let me know what you think. If you're enjoying this, you want it to keep happening, let me know. Otherwise, I might, for next week, I might get it soldered pre-stream. Alright, giddy up. Side the second. Gotta make sure we feed enough solder in there that it can wick under nicely. Oh boy. come on now. There we go. All right. Caps in place. Ready to go. Let's do this. Woo! That was a marathon session, if I've ever seen one. Crossing off our big caps, our big inductors, and our test points, and moving on to the testing. Hey Evan, welcome. Welcome to the stream, man. Okay, get the solder out of here. It's gonna take a moment, clean up the board a little bit so I don't get sticky every time I touch it. Oh, whoa. Apparently, isopropyl alcohol washes the part number off of these inductors. That was not a great, that's not a great design. Guess I'll have to be more careful. Wow, yeah. Yeah, so for those that are just getting dialed in here, what we're doing today is we're testing out some buck converters, and we're going to be doing line regulation, load regulation, a few different types of testing. I'm just going to be demonstrating how to take the measurements, looking at ripple performance, all kinds of great stuff. Yeah. So first part of this stream was just getting everything assembled. And now we are transitioning over to the experimental slash testing based approach. So the first thing we'll do is just power it on and see how it works. I am very hopeful. This design has been looking great so far. We got the kinks worked out with our 12-volt buck last week, so hey, this should be pretty smooth sailing. I'm gonna knock on wood with that. Never say things. Why do I say things? No, it should be pretty good. It should be pretty good. Based on what we saw last week, unless there's something terribly, terribly different, and I really don't think there is, with this versus the other design, we should be in good shape. Alright. First things first, current limited power on. And we'll just see how that goes. I'm going to set the current limit to around an amp. Feed it into DC input 2. Here we go. Buckle up. We got LEDs. That's good. Low current, not much current draw. Man, it's like Christmas up in here. Fets aren't particularly warm. All seems to be pretty kosher. Let's see if the voltage measurement agrees. Alright. First of all, we're in voltage mode. We're not in current mode. We got 12 volts is still 12. 15 volts is 14.77. I think that's right where it should be. There's our list of tests. Let me check the schematic comment on 15. Pretty sure we were just a little bit shy of 15. Pretty sure. Yeah, it says nominal is 14.79. So the 15 volt is kind of a misnomer. It's 14.79, and we're seeing, I think it was right around there, wasn't it? Yeah. Off by 2 millivolts. So yeah, that's right where it should be. 5 volt rail. 5 volts. Sweet. Yeah, so that's looking good so far. Looking over at our indicator circuit, you can see N2 ready is illuminated, and the 12 volt ready is illuminated. So that's pretty cool. Let's see, if we disable the 12 volt rail, so I'm going to switch over to current mode, and I'm just going to disable this by pulling the compensation pin low. You'll see 12 volt ready turns off. Sweet. So the 12 volt rail, oh no. Did I smoke something? What? What? Oh, come on. Whoa. Alright. What's going on with our 12 volt rail? What just happened? I have a feeling our high side FET just failed short. No. 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 Our FET's okay. Wait, did I just short out 12 volts to the comp pin instead of 0? Oh, that would be ridiculous. Okay, well, it seems that all the silicon here is okay. It's just... Yep. Not sure. Oh. Still in current mode. Still in current mode. Nope, that's ohms. Oh my goodness. Yes, our rough 2.5 volt references right on. Yeah. That's a little weird. Is this diode installed correctly? No, it's just... .75. Yeah. Oh boy. So this circuit's looking like it's not working. Let's just touch up the solder. NU20, I think. The N1. That's weird. Come back to our ground test point. Nope. Why is this monitor not working? 5 volts there, 5 volts there. 3 volts there. What do we got over here? Whoa. Whoa. What? What's this one giving me? Come on now. Don't be shy. How many volts? What are we reading? Seriously? 0? Well, that could be the problem. Do you just have a bum solder joint? 2.8 over there. 2.5 ref. 0. Man, it could be as simple as that. Just a bum solder joint. If that pin should be ground, what is that? I think that's pin 5 comparator. Oh yeah, pin 5 should be ground. So based on the fact that the ground pin was 3 volts, I have a feeling that solder joint isn't great. Yeah, that might play a role. Alright, let's try that again. Input 1. Power on. Hey! Works better when it has power. Right, so the in 1 is good. 12 volt monitor says, ooh, not so good. What voltage are we getting? I have a feeling I just blasted that controller into oblivion by shorting the count pin to the 12 volt rail. If anyone noticed, if I went to this test point, it was great. If I went to this test point, super not great. Yep. I really need to stop killing that supply. Like, for real. I'm out. This is the last one. I have no more. If we break it again, game over. Here I am trying my luck. Okay, well, had our gun. Let's go. I think one of the ones that I pulled off might not actually be broken. I think we've still got one to spare. But this supply is just filled with bad luck. I don't know. Any thoughts in the comments? So far, debugged one easy problem. Why our in one ready indicator was no good. That's how we intend to detect power fail. Or not necessarily power fail, but like if we've got 2 DC inputs versus 1. That's our primary detection method. Lets us know alright. Thinking very hard. There we go. Got it placed. Oh no. Knocked the cap off. Alright, we're pulling the heat. Just need to follow up. So there wasn't really any flux on that. Just need to follow that up with quick tinning, or using solder as a mechanism for delivering flux. Alright. Looks great to me. Let us see what happens. Cap looks good. Don't want to power down when it's still too hot. We'll be gentle. Maybe need like some kind of inrush current limiter or something. Maybe that would. Yeah. I have a feeling I shorted 12 volts to the comp pin, and it was not happy with me. 12 volts. Alright, we've got our 3 supplies, and I'm not going to break it this time, I promise. So now we've got the in1 ready indicator, we've got the 12 volt ready indicator, and now if I plug in the other supply, hopefully nothing blows up, and yes, we can see all 3. We've got 2 good DC inputs, and the 12 volt rail is good to go. Unplug the one, indicator turns off, unplug the other, so we can feed that information into our micro, and we'll understand whether or not we have one or both DC inputs ready to go. Looks like our ideal diode controllers are doing a great job of preventing backfeeding power, because if they weren't, that indicator would stay lit. So that's great. We've got the 2 DC inputs. If we see any of those lights turn off during our load test, that'd be a sign. Speaking of, let's do that. Yeah. So I want to set this up to 26. We're going to run it a little hot, just to make sure that we're pulling the power from this DC input. Then I'm going to hook up a load that will just totally blast that to oblivion, and we'll see if the indicator turns off. I hope it does. That'd be fun. One of the benefits of recording everything. Yes, regret. You can regret everything. Alright. So I'm going to do the test that we can do without the oscilloscope first, just to get those out of the way. Let's do a quick load test on the 5 volt rail. Let's see how that goes. Cool. Looks neat. Pulling some sweet amperage out of this thing. Let's add a little more load. Alright. Hey, look at that. So we hit the current limit. Oh, that's awesome. Oh, current limit's too low. Alright. So now we're limited to about 24 volts. Yeah. So this isn't great because our supply's got a fold back. So right now it's hitting the current limit. It's just barely hitting the ideal diode controller. But it's still enough voltage. That's not really how this is meant to be used. It's not made for being driven with this kind of supply. Alright, that's alright. We'll give it a proper 3 amps. Give it a 3 amps from the DC regulated supply, and then we'll give it this over here. Okay, so I need to grab a couple more multimeters. We only have one that's, I'll say, decent, but the other ones are good enough. These guys, you've seen them before from our other streams. I trust them well enough to do voltage measurements. I don't know that I trust them well enough to do anything else. We'll get them set up here. Do a quick power down, which takes a little more time when you got 2 inputs. That's okay. And we've got some of these great alligator clips that allow for yeah, just a box of multimeters, maybe 2 digits. Yeah, they're so cheap, you know. They don't time out, they just stay on forever. They're actually pretty nice. Alright, so let's see. Do you guys have any preference on what we test first? Feeling the 12 volt because we keep breaking it. No, I'm just kidding. I think the 15 and the 5. If that's alright with you guys. Do the 15 and the 5 first. It looks like you can't read that too well. That's okay. I'll read it to you if you really need to know what it's saying. Basically, we're just going to do some line regulation, load regulation tests, and yeah. Basically, just load it down and see how it does. In this case, for doing line regulation, the more accurate measurement we'll want will be operating voltage. So in that case, I think I'll want to use this meter for volts, and then we'll use this to get a rough idea of how much current's flowing. And I'll get ground headed back to the main supply here. Just gonna use the bananas right off of the DC supply. Perhaps I should be using local board ground. Alright, I'll use local board ground. Okay. And then we'll tap current. Oh, well, we wouldn't want to tap current off this. So we'll run the current back to the main supply. Alright, so ground, power, try to tap that off here. Oh boy, this is gonna get tricky. I wish I had 2 test points I could pull from. Mostly interested in transient performance, ideal diode controllers, line regulation. Yeah, cool. Yeah, we'll hit all that. We got line regulation, load regulation, efficiency, and transient response. So maybe I'll do the efficiency last. Just to get more of what you're interested in right away. There we go. 2 alligator clips on there. And we're going to need a heck of a lot of impedance. So in order to get this loaded down, we're supposed to get 3.3 ohms. What? That doesn't sound right. Oh, this is on the 15. So 3.3 is just one of these. We'll grab current. Alright, let's power it on and see how it looks. Oh, works better when you plug it in, doesn't it? Okay, so we are getting 0 amps. Oh boy, she's dead, Jim. Okay. All right then. Let's jump ahead to this other supply. We'll try the 5 volt, just like I said. Hopefully that wasn't the controller, hopefully that was the FET. Alright, let's try this one. Dude, chill. Sure not. There we go, getting 5 volts. 5 volts measured there, that goes back to there. Let's see if we can load this one without blowing it up. Alright, 0.7. 1 amp for the 5 volt line regulation. We should be getting 3 amps out. That's pretty close. This is the ground connection. Let's add one more. There we go. So now we're getting still 5 volts out. Got it loaded. We're at 26 volts in. And this is asking me to measure this at 26 volts in and 3 amps. We are pretty close. We are at 3.5 amps. I'll just make a note. We got 3.5 amps. And we have a measured voltage of 5.029 volts. We take this input, we scale it down. Yeah, JD. Oh no! Yeah, blew it up already. I'm guessing one of my clips was like, I don't know, touching something it shouldn't have been. Turning the supply down to 18 volts. Oh, you notice the in ready turned off. That's cool. So right around 21 volts is where the input ready flag flips. We're almost there. We're almost there. 18 volts. 18 volts. Yeah, JD's like, those lights are supposed to be on. No. Yeah. I'm guessing we blasted those FETs. Not sure why. Don't. But yeah. All right. 18 volts in. We're getting 4.93. We'll call it 7 volts. Still getting 3.5 amps. Obviously, we haven't changed the load. And I'll just disconnect that. As long as we've got this set up for a load, I suppose we could switch over and do transient response pretty quick. Yeah, why not? Why not? We'll kind of get each of these set up for the load and do it that way. Alright, got the calculator. This math is hard, okay? What do we got here? So we've got an input voltage swing of 26 to 18. 8 volt swing. On the output, we got a 5.029, 4.937. Got a 0.0, got 92 millivolts a swing. And divide that by our 8 volt range. Got a 1.1%. 1.15% change, so line regulation would be the inverse of that. So that's what, 98.5%? It's not bad. Depending on how you want to think about it, right? Change the input voltage, the output changes by 1.15%. I can't remember which way I'm supposed to flip it, but that's what the number means. For every volt, change on the input will change by 1.15% of that volt on the output. I want to just take a look when this is not under load, because I notice now when there's no load flowing, we're at 5.085 volts. And when I turn this back up to 26, at 24, 25, 26. Holy cow, yeah, so when there's no load flowing, yep, it is near perfect, which is not terribly surprising, right? We've got, yeah, not terribly surprising. Okay, so I've got the scope here. I'm gonna clear some of the bench space so I can get the webcam kind of over where it needs to go. Let's see how that looks. Not the worst. Not the worst. See if we can get that to focus. Let's capture some transient response. So I'm just gonna get the one channel going here. I think we really only need one channel. We get channel 1 set up for showing us the 5-volt rail. And I'm gonna try to get this hooked on there. There's a lot of clips hooked onto that. And we're gonna try to get ground hooked up. Okay, great. So now, just to show you what we got here, just got the oscilloscope probe hooked up across the 5-volt rail. And now in theory, we should be able to see this pretty well. We got the scope set to 5 volts per division. Let's do 2 volts per division. We've got enough divisions here. We'll do 1 volt per division. We'll get it set to -3 volts. Great. Let's force a trigger. Great. Trigger level up here. Horizontal position set. Alright, so sorry, I'm not doing a great job of explaining this. Basically what we're doing is we are setting the trigger level of this scope, as you can see right here, to just below the DC level. And the hope is that when we go in single shot capture, it never triggers. But when we do the load step, hopefully we'll see it dip down below that 5-volt range, and we'll be able to see exactly how it looked when we dropped the load step. Okay, that's the idea. Going in trigger mode, got a falling edge trigger. That's great. Yeah, so let's give it a shot. Just gonna set the input voltage to 24 volts since that's the nominal input. That's where it's expected to operate. And we've got the clip here, so I'm going to drop a 3.5 amp load and let's see what happens. Not much. Okay, looks like we need to edge that trigger level closer to where we are. What was that level? So, what? Oh, we're triggering on the wrong channel. Oh my goodness. Well, that'll do it. Force, run. Okay. So now we're gonna trigger at 4.8 volts. Let's try that again. Glare at 1 volt trigger. Glare, I know you can kind of see this, the tripod. Glare. Yeah, I'll have to find a better way to... I wonder if this has a display output that I could capture directly. Oh, that'd be sweet. Does it have like an HDMI out? No, it's got a USB. Wonder if I can use that. What does it have over here? Nothing. Yeah. Well, does this help if I tip it up? Because I can do that and that. Oh, that's way worse. That is way worse. I can try to point it over there. That actually doesn't look half bad. Super out of focus. Might be too close now. He's like, no, no, no. Oh, let's see if that might be as good as I can get it. I need like a fixed focus. You know what? I tell you what. Here's what I'll do. Give me just a moment here. I'll get the main camera looking at the screen. It's gonna make the transition take longer, but at least you'll actually be able to see what's going on. Alright, I'll give you a pick. You can have that. Is that better? No? Maybe? Yes? That? Here, let me tweak this a little more. I can get that better. I don't know. Yeah. Okay. Oh, you're gonna love this. Yeah, this is what you wanted. Yeah, you can see that very, very well. One moment while I switch. Boom! Now that is a scope you can read. There. Washed out. Ah, there's no pleasing you. I'm moving on. No corp likes it. Boom. Validated. Moving on. Anyways, alright, let's do the load step. Load step. Okay. Let's see. So we got it trigger set to 4.8 volts. Hoi! That's neat. It just looks noisy. Let's try that again. Yeah, that's really not bad. Maybe we're zoomed in too far. 500 nanoseconds? That might be. Let's get this on the order of milliseconds. Single shot capture. Whoa. Oh boy. Single shot capture. Whoa, trigger level set to 4 volts. Come on now. 4.9 volts. So that's just the extra ripple. That's what that looks like to me. Oh, JD says it's good now. Okay, so that must have just been the delay. That must have just been the delay. Okay, so wow, if that's really what the transient response looks like. Oh, you can see a little. You can see a little undershoot. Okay, well we know the DC level's good. So let's get out of DC coupling mode because we don't need that. Let's center that. Let's run. So now if we trigger here, one, you can see the output ripple. Wow, that is not a great trigger. It's not a clean signal to trigger on. No. I need to like adjust the hold off and stuff. Nobody's got time for that. Alright, so now we got a 50 millivolts per division. I'm going to set my trigger level down here. Set it to single. I'm going to drop this on. Oh, it did. Oh, it did. Okay. Okay, still triggered. Try again. Alright. Drop. Oh, bumped it with the clip. Okay. Oh, bumped it with the clip again. Okay. There we go. Hey, that's a load step. That's one to save. That's pretty good. I think we can do better. Wow, that's actually a pretty snappy control loop. If that was getting back to 5 volts as fast as I think it was. Whew! That's like, count the cycles. Wow, that's like 1 cycle, 2, 3, 4, 5. Like 10 cycles later, we're almost like fully recovered. Not to mention the full magnitude was only... So there's our 5 volts. Only 200 millivolts at the absolute lowest. That's not bad, considering we're going from 0 amps load. So this is one of the most, sorry about the fan noise. It looks 3D from here. Nice. Yeah, that's, no, this is actually an awesome load step because we're going from, wow. Oh my goodness, that recovers fast. So yeah, we're going from one DC level to another. And it recovers in 1, 2, 3, 4, around 4 switching cycles. This is a 300 kilohertz. Why am I even messing around with this? That's what cursors are for. That's where the load was applied. And that's where I'll call recovered. Woo! That is not bad. 10 microseconds. 10 microseconds to recover. And it's a nice controlled, yeah, that's, I've got no qualms with that. No, I mean, yeah, scope like this is just a general purpose. You know, it's nothing too fancy, but it gets the job done, in my opinion. So cool. I want to try a lesser load step. So I'm going to do a kind of medium load to a heavier load, so we would expect to see the transient performance be a little better on this one. So we're going from a 2.5 amp load to a 3.5 amp load. You can't even tell. You can't even tell. That doesn't look like anything happened. Like, sure, it triggered. That doesn't look like anything happened at all. It's just like a rogue. Yeah, that. Yeah, you can kind of. I think I just wasn't getting the trigger well because the range is so small. But look at that. That's awesome. So let's do. Yeah, there's a little bit more. That's a good point. We didn't capture the positive transient. Let's try that. Trigger menu, rising edge. Get the level set above. Single. Cool. Single. Oh, come on now. Get the load. Oh, goodness. Get it loaded. Hey, this is really being a pain in the butt. Come on now. There you go. Didn't capture that too well. Is that it? Is that the whole thing right there? That recovers even faster. There's that edge. Wow, that recovers fast. That's awesome. I think the magnitude's about the same. The magnitude of that's about the same. But the duration. Oh, but the duration, that's awesome. Because we are basically back to normal in 3 microseconds. I like it. Cool. Well, there's transient response on the 5 volt. No complaints there. That looks incredible. Let's do a quick efficiency calc while we're here, while everything's set up. We got a, what do we got? We got 24 volts in. We've got 0.93 amps in. So we got a 22.32 watts. We got, whoop, sorry about that. We got 4 point, oh goodness, fix one thing, break another. Got a 4.97, 67, I'll call it 66 volts times 3.33 amps. And that is 16. So I get a 16 divided by a 22. Oof. That efficiency. Only 74% efficient. That's not great. Granted, we've got some other losses in the system. We've got 2 more switch mode power supplies running. We're dropping some of that on the ideal diode. We're dropping some of that on the PTCs. There's 2 PTC fuses in series, so how much of that's being dropped on the PTCs versus the converter versus the other converter? I don't know. Don't ask me hard questions like that. I'm joking, obviously. I'm gonna just get the camera set up here so I can. Now we're gonna be in like super micro mode, so I've got to be able to switch back and forth between those two. So here's this. We're gonna get. Will you shut up? Apparently no. It wants to be really loud. Yeah, PTCs are probably gonna be a lot of that. If I really wanted to get fancy with it, I could take this ferrite bead up. I could feed power directly to the converter and take it before it goes through the second PTC. I just don't care that much. 74 means that this is probably running at 80, 85, 90, somewhere in there. But I'll just take down the measurement. So we measured 74% efficient at like a medium load level. Alright, let's power down. Let's do the same gamut. Oh, load regulation. Forgot load regulation. Never forget load regulation. Okay. So we got 5 volts. Let's see if I can get this somewhere in frame. Nope. Let's try this. Yes? Yes. No. Fail. There we go. So right now we're at 0 amps load, and we have 5.08. 5.08 volts. Load it down. Why aren't we getting a load? 3.5. 3.5 amps. 3.5 amps. We're getting a V out of 4.973 volts. Ripple voltage looks awesome. That was one of the things I wanted to note. It's what is that? From our previous test on the scope. Looks like we're getting around delta. Where is it now? Where's the delta? 70? Yeah, 70 millivolts of ripple. 70 divided by 5. Sorry. 70 millivolts divided by 5 volts is 1%. 1.4%. That's not bad. 1.4% ripple. Cool. And then to take the load step from 4.973, and one thing to note is that we're doing regulation before the PTC. We're doing regulation before the PTC. I might swing that over to the output of the PTC, and that'll drastically increase the load regulation performance. Because right now it's like we're making the 5 volt rail, but nothing's really connected to it. We're making the 5 volt rail, and then we're dropping voltage on the PTC. Yeah, better than a linear regulator, definitely. And so we'll be able to keep that stiff 5-volt rail, but then of course we're adding the frequency response of our PTC into the control loop, and will that impact it? I don't know. I haven't really dug into the frequency dependent impedance of a PTC before. I've never needed to, and I hope I never need to, so we'll see. We'll see where I end up on that. Anyways, for now we've got a 4.973, 5.08. That's a delta of 100 millivolts. Take that by the 3.5 amps, and we're looking at, even with the PTC in there, 3% load regulation. So obviously worse. So that's, if you change the load by 1 amp, the voltage will change by 3% of that 1 amp. Not great, not terrible. I'll allow it. Let's get this switched over to the 12-volt supply. And hopefully this one survives. Because we're already gonna have to scavenge if we blew up that controller. I'm hoping we didn't. That would really ruin my day. So it means I'd have to order some more parts from DigiKey to do the rest. Oh man, I thought I'd need a lot of FETs. I didn't think I'd need a lot of controllers. Alright, got that hooked up. What load are we targeting for the 12-volt test? We are targeting a load current of 4.8 amps, which is a 2.5 ohm resistor. Oh, thankfully I've got this resistor bank right here, rearing and ready to go. Just gotta get it hooked in. So what I'm gonna do is I'm going to feed this to both ends. That'll give us a 10 ohm resistor divided by 4. In other words, 2.5 ohm resistor. So that should be full load. Alright, let's try powering on. And of course, we blow it up. Why wouldn't we blow it up? Okay. Looks like it's time for some debug. Because that is super dead. So it seems like when we're getting up towards that peak of the load, something's happening. Maybe there's some ringing. Maybe there's some transient. I don't know. I don't know. Okay. Getting the... Oh boy. What's going on? It's like stuck. Okay. We're switching back to our normal multimeter leads. We need to find the fault. What is failing on this board? Yeah, that's what I'm... So, yeah, in that stream, the first NCP3020 was good. We pulled it off the board, and then put that one back on the board. Turns out one of these FETs blew off, so I took it back off the board. The problem is that it's in a pile of dead components back here. One of these is good, one of these is bad. If I had to guess which one was bad, or which one's good, I'd say the one with the flux on the bottom, because I know we reworked it with, I don't know. So I'm going to say that one's probably the good one. But I think we just blew up some FETs, hoping. Got it in beep mode. Oh. What's that now? Is that just the diode? It's getting a beep before. What's up? Why no beep? Oh, that's a shorted low side FET. That's a super dead low side FET. This one seems okay. Yeah, so looks like that FET internally became soup. Oh, that's no bueno. That looks okay. That looks like a diode. That's a dead short. That's a dead short. That's a diode. Alright, so it looks like both of the low side FETs blew up. Maybe I do need to adjust the peak current limit. It appears as though... Hey, JD, nice! You got the sticker, that's awesome. Yeah. Cool. Glad it made it through the mail. Oh. Yeah, I was thinking about dropping a piece of swag, one of our boards, in there. But that's something I needed to figure out, because apparently if you put something rigid in an envelope that is otherwise a letter envelope, it is no longer just a letter. It then becomes more expensive. And I was like, oh, I didn't plan on that. Let me know if you guys like this angle. I might try to work from a less top down, a more kind of triangular. Looks like the bottom right and side of the screen. What shorts? Are you asking which shorts they are? That was checking VDS, sorry. I'm used to just having the top down view where you can see everything and I don't have to think about it. That's kind of why I set the camera up that way, but the variable focus of a webcam is miserable for capturing. I need like a fixed focus webcam that I can use to really dial it in. DSLR might be a little overkill, but yeah, gets the job done. So it was a Q13 and a Q11. Those two parts are shorted to ground, which, as NoCorp was suggesting, might mean that our peak current limit should get dialed in a little bit. You mentioned that you'd calculated what the 100K would come out to. What is that peak current? Because I'm looking for a steady state output current of 5 amps. So I think I set the peak current limit to like 7. But I might have done like margin on margin on margin on margin and ended up kind of over constraining everything. It's being overly conservative at the end of the day and setting the peak current limit to like 100 amps. Yeah. So whatever. Yep. I'm glad I bought extra FETs. It appears as though we'll need them. Oh yeah, the sticker. Sticker. Yeah, it is. That is the logo. Yeah. Yep. Probably looks a little something like this. There we go. A little something like that. Oh, right. The RDS on. Oh, so I probably baked margin on margin on margin. Because I probably picked the worst case RDS on at the maximum junction temperature. Yeah, I should have probably designed that more nominal and less worst case. So our FETs are, what are they? Let's crack open the good old data sheet. Our FETs are the, yeah, there we go. DMN 10H170 SK3. Those are the FETs. speaking of, let's get a couple more of those. Let's get them on the board. I remember these aren't like the most spectacular IC from an RDS, or a spectacular transistor for RDS(on), but man, they're no slouch. It's not like I picked a particularly inefficient FET. It's just a good balance point between cost and efficiency, my perspective. At least that's what I was shooting for. Yeah. If I remember correctly, these are something like 100 milliohms nominal. I'm just hoping that when these failed, they didn't take the controller with them, because it shorted the gate, drain, and source. That would really be a shame if it took the whole controller with it. Yeah, so we're driving this with around 10 volts, so that's seems pretty good. 10 volts on the gate. I think 9 volts on the gate is more close, but we'll call it 10. Yeah. Alright. Oop. Sorry about that. Let's just make sure this is on there nice. Alright, we'll see. Could we bring it back just by replacing the FET, or was there more failure that came from that? Only one way to find out. It's powered on. Hit! Oh! Dang it. Yeah. So there's a 5 ohm resistor in series, but I mean, when you're clamping 24 volts. Oh, my inductor size, it's a 153 code. I think it's a 15 mic. I've got where is it? What? I thought it was right here. There it is. It's 15 microhenry. 153 is the code on top. Okay, well, let's try swapping out the controller. Since I've already killed the 12 volt one too much, let's try the 15. Yeah. Cool. Thanks, No Corp. It makes it a lot easier when I don't have to do the math. Joking. Yeah. No, it's just yeah, I have a feeling that if you take the worst case everything and you calculate out the value that I chose, it probably makes sense. But since our transistor is not at its maximum junction temperature, the current limit might actually be set for like 40 amps by the time you roll back to get to the nominal case, which is not necessarily what we'd like to do. Alright, getting this controller back on the board. But yeah, if that peak current limit isn't set right, yeah, I could always sacrifice some of the efficiency and add a discrete current shunt. There is some value to that. Because RDS-on is highly temperature dependent. So if I can get rid of some of that dependency on temperature, maybe good. It'd be good to do that. I don't know. Cool. Alright, it's down. The controller might have been broken before we started, but it's down. I like adding test points so I can cut traces and add shunts for measurement purposes. Not sure what you're suggesting. Oh, like if we add a known resistance in here, like if we add another 100 milliohms of impedance to ground, we'll know that we'll have that guaranteed 100 milliohms no matter what, plus the RDS on, so we can use that as a way to adjust but I'm saying like the RDS on, the rated RDS on, there's a derating factor based on how warm the IC is, and the warmer the chip gets, the higher the RDS on becomes. So if I was setting the peak current limit for 5 amps at the maximum RDS on, at the lower temperature of the FET, it would be, hopefully I don't have that backwards. I'm pretty sure that's right. Pretty sure it's a positive temperature coefficient. Pretty sure. Not positive. Pretty sure. Alright. Yeah, looks like that was dead. Okay. That is gonna put us dead in the water for today. Because I am just flat out of controllers. What? No. A dead short again? How did we break that FET already? No way. No way did we break that FET already. What? Were both the FETs bad and we just didn't replace both? The one ohmed out okay. What in the world? Alright, whatever. We'll take it one more try. Yeah, for RDS on. Yeah, add a current shunt so you can set a lower bound. Yep. That is absolutely what I was getting at. But I was like, hey, we can use this fancy, neat control scheme. I think I just need to think about like the error budget on that and think about how to bias it so we're not violating the safe operating area of these parts. Because maybe I really do want to just let that resistance change so our peak current limit is reduced as the part gets warmer. That doesn't seem like a bad idea. That seems like if the part's hotter, we're getting closer and closer to the point where they die. So maybe we don't want to push them as hard. Yeah, just a thought. Just so we don't exceed that instantaneous maximum current. Alright, FETs off. Something destroyed these. I'll power this on with the FETs removed. We're going to take a look at that. Alright. Let's take a look at how this looks. What voltage are we seeing on the gates? Comp pin is showing nothing. About a volt on the compensation pin there. Yeah, I was trying to figure it out with 5-volt converter, 12 V in. We got 24 V in. Less likely to kill the controller. Problem is the current limit is dependent on the input to output voltage ratio. Yeah. Yep, because that'll change your ripple current. Yep. Okay. 100K is reasonable. That's a shame because I'm blowing up the FETs. Curious, what is reasonable? What's the peak current limit on that? Yeah, it's not looking great. Alright. FETs are cheap. 4 more. Just put them on. Worst case scenario. I've confirmed that the controller isn't blasting the FETs into oblivion with 24 volts, so worst case scenario, the controller just doesn't work and we need to replace the FETs anyway. Best case scenario, one of these converters comes alive. Yeah, that's going to be like a hard stop for the rest of our testing too. Like, I really need to get these parts in order. Eight amps average current. Oh, I see. Yeah, we should only have 5 amps average current coming out of these. But, so I could probably pare that back a little bit. Maybe set it to like a high... maybe like an 80, an 86, or 75K maybe. Maybe I could get away with something like that. Gotcha. Yeah. I think it's something about, like... yeah, I think it's something to do with the load step. So when we're putting a heavy load on, maybe the peak current violates the safe operating area because the controller's trying really hard to, like, start up under a heavy load. Maybe it's just something simple like that. I mean, worst case scenario, if I pare back the peak current limit and we start to see the supply drop out of regulation at heavy load, we'll know that we've gone too far and it's time to turn around. We can experimentally verify, but I think based on the fact that we're practically blowing these parts off the board, I think we need to pare that limit back. I would rather err on the side of a supply that is reliable, even if it means that we need to maybe change the FET that we're using or tweak something else. I really, really don't want to have a UPS that struggles to not blow up its 5-volt regulator. That sounds like no fun. Alright. Let's finish these off. I have a feeling both of these controllers are dead as a doornail. Wow, those two set it on really well. These two seemed a little starved for flux. Okay, let that cool down a little bit. That is smoking hot. Yeah, I'll have to, let's see, what do we have in the high tens of ohms? We've got a 900K or 90K. We got an 8.7K or 87K. We've got a 64. So we could try the basically 70, or we could try the 90. Maybe I'll do some math and throw in a couple new resistor values with that order for the controllers. We can play around with that a little bit experimentally. Yeah. Okay. Yeah, so the 5 amp output. 5 amp output, we'd want less than 95. Okay. Interesting. Okay, that's cool enough that we're probably not gonna blow anything up. Let's see if one of these comes alive. Nope. Need new controllers. Need new controllers. Well, at least we got to do the transient response on one of them. 1 out of 3 ain't too bad. It's a shame about those parts, though. Just gonna take these off so I don't forget. Yeah. Man. Well, thanks for watching, you guys. Sorry we got cut a little short, but I am flat out of these controllers. I only ordered 6. I figured a margin of 2 would be plenty, but yeah, I was wrong. I was wrong. Yeah, seriously, thanks for hanging out in the shop. I'll definitely take a look at the math for what we should be changing that peak current limit to. This is pretty unexceptional performance. But we'll get this straightened out. A couple of resistor values to kind of dial in the point of not tripping before we should when the FETs are warm, but still protecting them when the FETs are cool. Just need to pick a more reasonable operating temperature where I'm running the calculations, and that should help a lot. Because what's happening is we're just heating up we're violating the safe operating area of these parts. They're internally shorting. and that's back driving our controller with 24 volts. Then the controller bites the dust. So yeah, it's really a shame. It's cool that we got 5 volts though. Seems like that peak current limit's fine for that, but hey, maybe not quite. So what we'll have to do is just kind of dial in that 5 volt operating point and see how close we can get, see what those 3 should be. Neat stuff. I'm still content with where we're leaving this. I got that in1, in2 indicator. That's pretty neat. Yeah. Don't forget your... Oh. No, I won't. No, I won't. You want the proper outro? Is that what you're asking for? Yeah, forward progress. Declare victory. Yes! You know, before I go, I think that's a good point, right? To the untrained eye, this might seem kind of like a failure. This might seem like a, oh, wow, there were problems, and that's bad because it means the design doesn't work. Actually, you know, these kind of little glitches, these are... You know, this is a sneaky calculation, you know? This is a mashup of the physics that you know for, like, circuit theory, and then you're also playing with some semiconductor physics, and you gotta track these variables, and sometimes design margin leads you in the right direction, but in this case, the design margin that I was calculating, I was adding in design margin to make sure that we wouldn't be tripping the peak current limit too early, and I just assumed we wouldn't hit the safe operating limit of the part. That's a pretty strong assumption, you know? Turns out that assumption was false, but now we're able to debug that, and we're able to fix the problem when we're dealing with a prototype and it's really easy to get at, and not when we have a full UPS installed in a chassis with 4 daughter cards and we got high voltage around. This is a much more convenient platform to debug the issue, and yeah, I 100% agree. This is not a failure. This is a small stumble, but overall, it's a victory, right? Confirmed that this little monitor circuit's working well. We're able to do transient testing and gain some confidence that the control loop was tuned competently. Like, that was excellent transient performance. Overall, very happy with this design. Just needs a little bit of refinement. So, yeah, thanks for all your help in the comments. As always, JD, No Corp, thanks for shouting out ideas and helping us along this journey. For now, just want to thank you guys and hope you learned something great today. Yeah, hope to see you again soon. Thanks for watching. Bye.